Hi, welcome to the lecture for Python for physical chemistry. There are many students, especially in my class, who is learning physical chemistry using the textbook by Silbey, Alberty and Bawendi, 4th edition in particular. We have a number of problems intended being solved by computer code. Well, actually those problems we can solve them by Mathematica or MATLAB and the like, so-called computer-aided system program or softwares. But instead, I found recently that a number of students, freshmen in particular in my university, are learning Python. So it would be a really good idea to use Python to solve such problems. Or basically, the drill enhance their ability to problem solving technique, and also that will deepen their understanding of the physical chemistry idea. So, but a number of them have some difficulty just to start with. So this is the first problem. I mean, this lecture will solve just the first problem of the book, and then guide some student who is really at the beginner how to install Anaconda Spyder editor in particular, and then use it to solve the problem 1A and 1.7 of the physical chemistry textbook. Okay, let's begin. Firstly, what we need is of course Anaconda, so which is free. So I will just go to their website, Anaconda. Well, actually I had already typed it. So Anaconda website, and there are things like individual edition, team edition, enterprise edition, but we just don't care, then we'll just get in the individual edition. I just say download now, and then not sure, yeah, okay. And download, there are individual edition, and for Windows there are actually I'm going to get Python 3.7, which is the recent one, and then I'm using Windows, so I'm going to get 64-bit general installer. So just click or double click, and then it downloads. So when the download complete, and you just double click the icon, and then it'll install. There are not really many questions you have to answer, just to install as default, and that will be enough for you to start. I already did that, and actually I did a Korean lecture previously, so I already did that. So I'm going to just exit, and we'll launch Spyder editor. I could do from window prompt. There are actually I made a kind of shortcut here, or in the Anaconda there, you can launch Spyder Anaconda 3 from here. So anyhow, either way, you launch Anaconda, and I'll close the Chrome browser. So we'll just exit, and then it takes a while to load the Spyder editor. Yeah, it's coming. So you just install and just to launch Spyder editor. Well, in the previous version, as I remember, you need at least a couple of packages, Python packages, especially NumPy, Python, NumPy, NumPy, and also a plotting library, and maybe Panda, which is kind of a spreadsheet package, and yeah, as such. So if you at this version of Spyder 4 or Anaconda 3 distribution, those are kind of installed in default. If not, well, it might be different from version to version. So if not, you may install those packages, those you need, either from Anaconda PowerShell prompt or I'll just use a PowerShell prompt or Anaconda prompt. So it's just like a command line prompt, and then there you can do pip command. I think it's Python install program, something like that. So anyhow, install and say numpy. So it will install numpy or check if there is a numpy available. I think it's there already. So, but it says that it's already there, so I don't need to bother with it. So anyhow, the kind of message you can, the first thing you can check is that just to say import numpy SNP. Actually, we will use many times of numpy, so we'll just kind of a shortcut or abbreviation of it as NP. So if I do this, and then that is a one line kind of code. So here we just launch it. So this is the editor. Let me briefly explain what are those. Okay, this is the editor window. Okay, and this is the console window. Well, let me just explain a couple of things on assuming that you are just it's your first time to look at this window. Look at this Spyder editor. So here it says that Spyder Python 3.7, and then this is a default or working directory. This is the working directory. Okay, it does not really. This is the working directory. This is the working directory. So here it says, let me switch this to arrow. Here it says that user Andreas, meaning is that this is kind of a user directory. So I usually use here as P-Chem _py, where I write the code for, of course, for the problem, to solve the problem, and then I can store any material or any code and other data set in that directory. So this is the working directory. You may change this working directory for your own work area. Okay, so that's one thing. And there are many icons here, but basically what we need as a beginner, this is the run button, which runs from the beginning to the end. Whatever code written or included in this the editor window. This is the editor window. Okay, editor window. And then there is a very interesting feature of this window is that actually there are this button. There is this button. This button actually runs a section of this code. Meaning is that you can develop a part of the code and then test it and then move on. Okay, so let me show you how it works a little bit later. And then this is the console window. So you write the code here and then run it either with this run icon or running section icon, and then the running result comes out in this console window. And then you can also type Python code here. One way you can do is that you write the code here and run some section, and then here you may change some variables by just typing your input, and then run the other section. Then you kind of runtime, not really runtime, but at the time it's running, you may change the value of the variable so that you can exercise or you can check various things of your problem. Okay, so basically what those are. And then this window, there are many things, but variable explorer, meaning is that of the code you can kind of look into what's the value of each variable or array as such. And also there is a help window, just like that. Okay, so I'll just erase this one, and then let me explain what's the problem here. So problem is this one actually. So I need the pen again. So we are going to solve problem 1.7 and one point A. Two problems. Actually, those are kind of tied together. So firstly, what it asks us to do is that for hydrogen at 0 degrees Celsius, okay, and then it gives us the molar volume at such bar. So 4 pressure point is here, and then the molar volumes are these, okay, 4 molar volumes. Obviously, higher pressure, you have smaller molar volume. So that's kind of behavior like this. And what it's asking is that second and third virial coefficient. So what you need is that basically Z, well, actually there is a better things, okay? So this is the compressibility factor. Compressibility factor and per mole, so PV bar of RT is the compressibility factor. And this is the Virial equation. So compressibility factor is expanded in terms of as a function of 1 over V, reciprocal molar volume. So first term is 1 because this is the ideal gas value. And then for the real gases, B and C are not 0. So this is the first term and second term. So this B is the second Virial coefficient and this C is the third Virial coefficient. So what you're given here is that you are given the pressure. Let me switch to pen, and then maybe a red color. You are given with the pressure and then V bars, okay? And so basically you have two, temperature, also you are given the temperature. So temperature, pressure, molar volume, and R is a gas constant. And then this number is given for each point of the pressure. And then, so you plot this compressibility factor as a function of 1 over V bar. And then you plot it. For example, you plot such, and then make a fit of it, fitting this plot, and then the best fit will yield you B and C. So from the best fit, you figure out the virial coefficient. That's the problem. And then utilize this equation, Virial equation, for the given pressure. You will calculate this V bar. Okay, but that is cubic equation, so you need to solve either. You need two things. Firstly, you need a way to fit this data point. So we are going to use NumPy routine or module, which is polyfit. And also, this will end up with cubic equation, so we are going to need a cubic equation solver. In general, polynomial equation solver. So we are going to use the NumPy roots module or subroutine. Then that will give us a result. Okay, so basically that is okay. Let me go back. And so I didn't explain. Yeah. And then what it is here is the second 1A problem is that utilizing this B and C Virial coefficient, then you have a Virial equation. Then at the given 75 and 150 bar, you are going to obtain V bar corresponding to this pressure. Well, as such, as I said, that will be your cubic equation. Then you have to solve the cubic equation. Of course, it's easy with Python. Okay, so we are going to just to do code and then run the code and get the data, get the kind of result, and then that's it. Okay, so let's begin. Okay, right. Just let's clean this, and then firstly, it's really good or great idea to have your code commented properly or maybe generously, I would say. So what I usually do is just to at the beginning, I just to do some comment. Comment is not a part of the code. Well, actually, that is most important part of the code. but which does not really do numerical wise. Actually, computer does not really number crunching for the comment. Comment is just there to help yourself. So as I said, give generously and then nicely the comment. So in Python, actually the basic grammar and other about the Python itself, you'd rather learn it from a textbook or from internet or from any other source. There are abundant source. I'm just helping you how to start, to begin to use Python and utilize Spyder editor to solve physical chemistry problem. That's what we are doing now. So this pound sign is prompting the first column, first character of the line. Pound means that the rest of the line is comment. So basically what I wrote here is the Silbey Physical Chemistry 4th edition, chapter 1, problem 1.7 and 1a. So this is the code to solve this. And then firstly solve the problem 7 for the second and third Virial coefficient for H2 at 0 degrees C. And molar volumes are given as such pressure. And secondly, we calculate the molar volume of H2 at 75 and 150 bar. Okay, and then compare with it the ideal gas value. So we need to calculate the ideal gas value too. And it says that numpy pole fit and also numpy roots will be used. Okay, so this is a kind of brief comment, but will be enough. And by the way, pound percent 2%, pound percent. This is a kind of special comment, meaning is that it will make this up to here to the next pound percent. That is a chunk of the code which will be run by this button. Let me get that. This button. Okay, that button. So then you just separately out of your entire code, certain sections you can run separately. Okay. So then next, after the comment, what we will do, first thing in the code, what we usually do is, well, actually I will just make a separation of this. Well, actually not really need to do it, but another pound, and then you notice that this section and that section are separated. Okay, there is a kind of the horizontal bar is here. So next thing we could do is to import numpy as np, and also matplotlib.pyplot is a module as plt. So we will need two module to run the code. You can think about this as a subroutine, okay? Just to code it and then it does work for you. Okay, so this thing. So let me just run quickly this one. Obviously there is nothing, so it says that nothing to excuse because all are comments. And then we'll run the second, and then it says that, you see here, it ran the second chunk and then it finishes because it just did the work. It does not give you any adverse message like numpy not found as such. So you are safe now. We are safe now. And then we are going to solve problem 1.7. By doing so, we will do firstly we'll make another chunk of code like giving this. So this is a separate part of the previous two chunk of code. So problem 1.7, and then we are going to use the gas constant with not ATM but liter bar per mole K, okay, which is 0.083145, okay, and then T is the temperature 0 degrees Celsius, but we are going to use absolute temperature, and then which is 273.15, and then maybe some other values given in the program. I'm sorry, in the problem, and those are as such, I will just do I firstly initialize p bar, which will be done in the problem 1a. We'll do two pressure point there. One is 75, the other one is 150. I'm putting this one before I'm running the chunk of the code which will run the calculation for V bar, so that later on I can change the P bar and then run that particular chunk to obtain another molar volume for another pressure. So I just did the P bar here on purpose, and then we have 4 data point given in the program. I'm sorry, in the problem, and then np.array generate array, one-dimensional array, but in Python they say that it's list. Okay, so it's a list of numbers, something like that. So anyhow, I would know it's an array. So, and then I put a 1.0 here as a placeholder, because for the compressibility factor for the ideal gas, which is 1 for any temperature, so I'm going to give any pressure, so I'm going to give zero pressure compressibility factor. Zero pressure meaning is that V is infinity, then V bar over 1 over V bar equals 0. So 1 over V bar equals 0 will have compressibility 1. So here I just give the P value 1. It's a placeholder, and molar volume is 100. It's just a arbitrary number. We'll replace it with some other value like 0 and 1 later. Okay. Then 50.7 bar, 101.3 bar, 202.6 bar, 303.9 bar, and then corresponding molar volumes are 0.4634 liter and such liters. Okay, and then what we are going to have the Y value, which is reciprocal molar volume. Then this is the very conveniently done for the array. In Python, you just do this type of calculation, the expression, which will give you individual element-wise division. So which is just the reciprocal of each element and contained in this array. Okay, Y. Okay, so Y is reciprocal volume. Now we are at the point to calculate the compressibility factor. Okay, so compressibility factor is calculated in such a way that you see compressibility factor is, how do I do that, which is PV over RT. So R is a gas constant, T is fixed here, so R times T reciprocal, we say just denominator, and then that is multiplies to Pn Vm. Vm is just here, the molar volume, and the pressure is in this case the individual list here, and then that will calculate the compressibility factor Z. Okay, that is basically this is basically what it is that G equals R times T, or actually RG in this case. No. Actually, P times V over R times, actually R times T. That is the relationship. So we are just doing this. And now generate the compressibility factor. Now you remember that the first item, in this case in Python, the first element is indexed by 0. So Z0 and Y0, there is a special value. So when meaning is that Y0 equals 0, then Z0 is 1. So that's because at the infinite at the zero pressure, actually the V is infinity, then 1 over V bar is 0. Then the compressibility factor that behaves as an ideal gas, so compressibility factor is 1. Okay, so we just manually set this number. Okay, now we have both Z and 1 over V as a variable. List of array Y is there, so we are ready to call forfeit, yeah. So just one call for np numpy dot forfeit will do it. So that will return that this will return the coefficient of this second degree polynomial. In this case, 1 plus A over V bar plus C over V bar square. But in this case, it returns the higher degree first. So it returns P0 as C, P1 as B, and it should be 1, but value close to 1 is returned as P2. Okay, 0, 1, 2, yeah, that's right, 3. So now at this point, either you could check what's going on by printing out your value. See, just like print, then it will show what's going on or how it is done. Okay, so let's run this part before we go further. Okay, so we have run this, and then now we'll run this part. Okay, so I have a cursor in this section, then I'll just click this, and then this is run. It's very quick. So the third part is ran here. Okay, yeah, and then I print out Y, Z, C. So this is Y, and this is G, and C, that is returned from the polyfit. So this is the first element is C or gamma. This is the second element, which is alpha or A, and this is 1 that close to, this is close enough to 1. Yeah. So this is C. This is B. Yeah, that's right. Yeah, it's the third virial coefficient and second virial coefficient. Okay, so we basically we just did problem 1.7. Now we have that formula, we have the virial equation. Now we are going to solve a polynomial. I would say using numpy roots subroutine. So problem 1a, we are going to solve this equation. This is the virial equation. Remember that we have a virial equation just like this. Yeah. So, but we you see C2 is 1 actually, close to 1, and C1 is B, and then we multiply with 1 over B bar, and then C0 C, well actually the C0 or P0, yeah, is actually the virial coefficient, third virial coefficient, and then this close to 1. So this is the equation we need to solve, given the value of P, and we are going to obtain V bar. But the problem is that we multiply both sides with V bar square, then you are going to end up with V cube. So it's a cubic equation you are going to solve. So multiply by V cube each side, you are getting, let's look at that here. Okay, you are getting P over RT V cube plus you move this to the other side, then minus C2 V square, move this the other side, and then minus C1 V, and then move this the other side, which is C0 equals 0. So this is the polynomial or cubic equation you need to solve, and then we are going to collect the coefficient of this polynomial. Okay, these are the coefficients. So firstly we generate an array. Okay, an array. All right. So what I need to do is generate the array. So it's a 4-element array. Then A0, the first is this one actually. So P bar, which is given as in the problem, like 75 in this case, which was set up there. Okay, and then over T, and then P1 is minus C2, and A1, I'm sorry, A2 is minus C1, A3 is minus C0. So given the coefficient, then we are going to solve the problem by just call NP root or NumPy root. So NP root, because this is calling the NP root, and then it prints the result. Okay, that's done. Okay, and then the problem asks you to compare with an ideal guess value. So ideal guess value is easy in a way that you just compute V bar equals RT over P. So you just calculate RT over P, which is done here. So it's a kind of really nice kind of print out what is printing out, what is being printed out. So ideal gas volume at such, which is temperature, and then pressure, and then which is liter per mole. Okay, so we are going to put print out T P bar, and then RT over P bar. So that's ideal gas value. Okay, so let's run this one. So how we do that? Click this one, and then that runs, and then it generates. So first is actually is from this one, this line, and then by calling np.root a with the coefficient, it returns the solution 3 root, and in here 2 are complex numbers. J here is at I sign and minus root minus 1, and then another complex number which could not be a volume. This is 0i or 0j, then this is a real number and positive number, so this is the answer. So answer is that 0.3173 liter per mole is the answer, and the ideal gas volume is at the 273.15 K, and 75 bar is 0.3028 liter per mole. So which is close, but this is more compressed. Okay, so that's what is done. And then you remember that at this point, if I change P bar equals to 150 over here, so P bar is now not 75 but 150. So then let's run this part again, and that ran, and then that calculate 150 bar. So at the ideal gas value is why it's not showing? Ideal gas value is 0.1514, okay, liter per mole. And here also you have 2 complex root and then 1 real root which is positive, so that is 0.16625, and which is this value. Okay, less compressed than ideal gas. Okay, so I think previously also less compressed than ideal gas. Okay, so basically these two runs generate the answers for the question 1A. So we just solve both problems. And then more interesting thing is that, or kind of a handy thing you use Python, is that you can plot and then see what's going on. Okay, or you deepen your understanding about your equation. So basically what you can do is, firstly, we will prepare the data to plot, okay, for plotting. So what we can do is that we just prepare for plot in the next section. So plotting is done in such a way that interesting thing, or there are many ways, but one easy way to plot is that you generate numbers in the x-axis. Each point, each data, you generate each data point. So here we are going to plot from 0 to 15. Meaning is that this is the reciprocal volume. So this is the infinite volume, meaning is that this is zero pressure and higher pressure, okay? So, and then from 0 to 15, we are going to put 151 data point. So I guess then the kind of division is 0.1. And then this routine, NP routine, NumPy routine, line space for short, I guess, line space, and then xini, xend, and nx will just generate that equally spaced x point. Okay, so that's your axis point. Then now you are going to plot your compressibility factor, or your Virial equation. Your Virial equation as a function of x. So firstly, you generate y point. Then here we could just call it FV function point, the same number as the x data point. And then for each x point, we are going to calculate based on the using that Virial equation the y point. Okay. So how we do that? Okay, that's done here in this way. I'll just type some. Okay, so this is the Virial equation. Remember that C2 is 1, close to 1. C1 is the B or beta, and X is the reciprocal volume, and then C2 is the gamma or C, and reciprocal volume square. And then this is the calculation done. So you generated y value. So you have x value, y axis, y value, then you are ready to plot. So in order to plot, you are going to use plot library. And then, I'm sorry, that's not. Plot library. Use the plot library routines. You could do just like this. So let's do plot. Did I run this one? Not yet. I didn't. Yeah. So we'll just run this first. Done. And then we call plot as matplotlib.pyplot as PLT. So PLT that means that the routine is coming from this package. Okay, matplotlib.pyplot. Okay, so plot PLT plot. We first plot FOV or FV as a function of x, and then use the color blue, and then label is the Virial equation. Okay, and then scatter routine. You see, z is the compressibility factor, and y was the variable reciprocal molar volume. So we basically put the data point given in problem 17. Okay, just to see how well it is fit. Okay, and then x-axis level is 1 over b. Actually 1 over b bar. I don't have the over bar. And y level is PV over RT, or compressibility factor. And the legend, this legend will be put kind of best place figures, and then PLT show will show the plot. So let's run this and see how nice it is done. Oh, this is terrible. There is something not really good. Well, I just debugged that I mistyped or missed this line. So I just put it back and then run this section, and then it ran, and then we'll do plot again. So that plot is done this way. So let's look at this, and you see the data point, this one, and then I think that I'll have better way or the better color. So this and that and that and that is the data point, other data point given, and this is the kind of known in a way that ideal gas point, and then that's the fit. This is really good fit, so that we have really good answer. We answered perfectly the 1.7 and 1A problem. So this is a way you can approach the computer problem in the physical chemistry textbook. I emphasize to my students that it is very important to have such capability in problem solving, and then you may apply your technique or the way you approach your problem not only in physical chemistry but also all kinds of your research and your maybe personal problems too. So thanks for watching, and then God bless you. Thank you.